72 hours of chaos in space and on Earth. For 3 days, the sky and the ground staged a double act that felt impossibly coordinated. First, observers in the southern hemisphere reported a bright nova in Centaurus, a sudden stellar eruption that pushed a usually invisible star into the edge of naked eye. Visibility and lit up professional and amateur feeds alike. Hours later, another nova triggered alerts out of Sagittarius, sparking the same frantic chain of telescope pointings, gamma-ray checks, and instant social chatter among backyard astronomers and survey teams. The discoveries weren't whispers. They were loud, data-backed detections that forced satellite missions and ground arrays to reorient and log every photon. While the sky was erupting, the planet under our feet was not idle. Seismographs lit up over Venezuela. A powerful magnitude 6 event shook communities in the northwest, followed closely by strong aftershocks that kept hospitals and emergency crews on a knife's edge. Reports from international seismic agencies confirmed the intensity and breadth of the shaking, and the tremors were widely felt across neighboring regions, and threaded through all of it was a solar storm, a coronal mass ejection racing outward from the Sun just as an interstellar comet, known as 3I Atlas, passed through the inner solar system. Multiple space and science outlets flagged that the CME's path was projected to intersect the comet's trajectory, offering a rare, live experiment. How does an interstellar visitor react when blasted by a concentrated wave of hot plasma and twisted magnetic fields? 2 explosions light up the sky with no warning. 2 separate novae were reported within the same multi-day window, each detected by surveys and followed up by professional and amateur observers. One, catalogued as V1935 Centauri, Nova Centauri 2025, reached roughly naked-eye threshold brightness shortly after discovery. Optical detectors and space telescopes registered fast, high-energy signatures consistent with a thermonuclear runaway on a white dwarf. The second V7994 Sagittari produced a similar rapid optical brightening and triggered X and gamma-ray follow-ups. These detections were not speculative. Automated alert streams, satellite high-energy triggers, and ground-based photometry all converged to confirm both outbursts in rapid succession. Scientists' assumptions and immediate interpretations are cautious and methodical. The leading working model for each event is a classical nova. Hydrogen-rich material accreted onto a white dwarf ignites in a runaway, ejecting shells of gas at thousands of kilomostia. Where gamma-ray or hard X-ray detections occur, researchers infer strong shocks in the ejecta that accelerate particles. That's a key observational clue used to classify the eruption's dynamics and energetics. Amateur contributors were crucial. Backyard time-lapses and small telescopes provided early magnitude estimates and continuous light curves that filled in gaps between survey exposures. That grassroots data mattered for early spectroscopy scheduling. For video narration, stick to crisp factual lines. Both novae were confirmed by independent instruments. Both produced multi-wavelength signatures that point to energetic shocks. And the near-simultaneous timing is what pushed these detections from routine to newsworthy. Twin quakes hit Venezuela as telescopes. Freeze seismological networks recorded a pair of major earthquakes in the Zulia-Menia Grande region of northwest Venezuela during the same short window. Reported magnitudes clustered around the low 6 range. Reports vary between roughly 6.2 and 6.5, depending on agency and preliminary updates. With shallow focal depths noted in several catalogs, the sequence included strong main shocks and numerous aftershocks. Initial local reports described evacuations, structural damage in some communities, and first response medical activity. International monitoring services, USGS, EMSC, and regional agencies posted rapid event notices that seeded global seismic catalogs. Seismologists' working interpretations are standard but important. The 2 large events appear to represent a primary rupture, followed by nearby failure on an adjacent segment, a classic stress transfer pattern. Models used in early analysis focus on fault geometry, depth distribution, and Coulomb stress changes to see whether the second event was likely triggered by static stress changes from the first. Emergency planners emphasized the human impact. Shallow magnitude 6 ruptures can cause concentrated local damage, even when regional effects are limited. Field teams and engineers prioritized reconnaissance, rapid structural assessments, and aftershock forecasting to guide rescue and stabilization. A solar eruption meets an interstellar. Visitor space weather monitors observed a coronal mass ejection (CME) from the Sun that, according to propagation models, moved through the inner solar system on a timeline overlapping the path of an interstellar object. 3I Atlas. Multiple outlets reported forecasts that the CME's plasma and magnetic field envelope would cross 3I Atlas's projected path around the same days the novae and earthquakes occurred, creating a rare opportunity to see how interstellar material behaves under intense solar wind assault. Observers triggered coordinated monitoring. Radio arrays, optical imagers, and spaceborne instruments were tasked to watch for tail erosion, sudden brightening, or disconnection events. Scientific assumptions here are hypothesis-driven and conservative. Heliophysicists expect a CME impacting a cometary coma to strip volatiles, reshape the tail via draped magnetic fields, and possibly induce transient emissions as charged particles interact with ejected material. If the object is an interstellar comet, those interactions can reveal composition and physical properties that are otherwise inaccessible. Instrument teams also flagged operational concerns, protecting sensitive detectors from enhanced particle fluxes while still collecting high-value data. The result is both a safety calculus and a scientific sprint. Point everywhere you can without risking instruments. In voiceover, state the CME 3I Atlas overlap as a modeled intersection, then summarize the hypothesized physical effects, tail erosion, disconnection, transient emissions, and why that matters for composition studies. Stacking the odds, less than 1 in 1,000. Scientists' take. When independent rare events cluster, the first scientific step is statistical assessment. Each event here, 2 novae of notable brightness, a pair of magnitude 6 earthquakes in the same small region, and a CME intersecting an interstellar object's path, has a low individual rate. Multiply independent low probabilities, and you get extremely small joint probabilities, which is why early commentary used phrases like 1 in 1,000 or rarer. But statisticians immediately temper that with important caveats. Observation bias and clustering heuristics can make rare coincidences appear more significant than they are. Models like the Poisson point process and the clumping heuristic are standard tools to test whether observed. Clustering exceeds what random chance with current monitoring coverage would predict. Scientists' practical approach is process-driven. Compute baseline occurrence rates for each phenomenon over comparable windows. Simulate expected coincidence rates under null assumptions and then look for deviations. They also examine reporting windows and instrument sensitivity. More detectors mean more chance observations. Where physicists or geoscientists suspect a causal mechanism, for example, solar activity modulating atmospheric electrical conditions or triggering geophysical responses, a controversial and generally weakly supported link, they attempt to identify plausible physical pathways and testable predictions. So far, there's no established physical mechanism that causally links novae and regional earthquakes. Hypothesized solar-Earth coupling mechanisms are regarded skeptically and require robust evidence. Narration. Tip: present the raw improbability, then immediately give the statistical context and the method scientists use to decide whether something is noise or signal. Minute by minute, how the timeline unfolded. Key timestamps and data streams. The cluster played out as overlapping time-stamped alerts across different monitoring systems, telescope surveys, gamma X-ray satellites, space weather models, and seismographs. The quick confirmed sequence looked like this in broad strokes. Survey telescopes flagged an optical transient, nova, and follow-ups recorded multi-wavelength signatures. Roughly the same day, seismic networks posted magnitude 6 events in Venezuela with shallow focal depths and immediate aftershock sequences. Within the same modeling window, heliophysics centers issued CME propagation alerts that intersected forecasts for 3I Atlas's trajectory. Each feed carried universal timestamps that made cross-referencing possible, enabling scientists to line up observations and rule out simple timing errors or delayed reporting. Operational assumptions guided early decisions. Observatory teams prioritized rapid spectroscopy of the novae and high-cadence imaging for transient behavior. Space weather analysts reran propagation models as solar wind speed estimates updated. Seismology centers issued revised shaking maps and aftershock forecasts as new data arrived. That simultaneous minute-by-minute pressure required different communities to share timestamps and raw data quickly, so each group could interpret their own signals in the context of the others. The practical outcome: faster identification of meaningful coincidences and quicker rejection of false correlations caused by reporting lags. For narration, present the timeline crisply and emphasize that the time-stamped data streams are what let scientists test connections rather than rely on intuition. What makes 3I Atlas different from every other comet? Measured facts and working assumptions. 3I Atlas is confirmed as an interstellar object, the third of its kind detected after Oumuamua and Borisov, and that status changes the scientific stakes. Observational facts to use on camera. It was first detected in July 2025 by survey telescopes, exhibits a coma and tail consistent with cometary activity, follows a strongly hyperbolic retrograde trajectory, indicating an origin outside the solar system, and astrometric analysis suggests a comparatively large nucleus, orders of magnitude larger than earlier interstellar visitors according to publicized estimates. Those size and motion observations mean interactions with the solar wind will be faster, and it may produce more dramatic transient signatures than typical short-period comets. Scientists assume several testable things. One, because 3I Atlas appears massive and fast. Its coma may respond quickly to solar forcing. 2, spectral measurements taken during the CME encounter could reveal exotic isotopic ratios or volatile species not commonly sampled in solar system comets. Checklist 3. The lack of measurable non-gravitational acceleration in some astrometric runs implies a large mass nucleus size, but that inference depends on model assumptions about outgassing behavior. Teams are therefore prioritizing spectroscopy, radio monitoring, and high-cadence imaging to capture any transient that reveals composition or structural response. Narration angle. Highlight confirmed interstellar origin and size trajectory facts. Then list the scientists' clear hypotheses about what the CME encounter could reveal. Is this random chance or a hidden pattern? Current scientific posture and next steps. At present, the scientific posture is deliberately neutral and investigative. Observed clustering demands 2 tracks of work running in parallel: statistical vetting and physical hypothesis testing. Statisticians compute expected coincidence rates given detector coverage and baseline event frequencies. Heliophysicists and planetary scientists test whether plausible mechanisms exist that could link solar activity to increased rates of other transient phenomena or to geophysical triggers. Most proposed physical links remain speculative and require careful, reproducible evidence. Meanwhile, seismologists and astronomers focus on domain-specific follow-ups that either reinforce or undercut possible connections. Immediate next steps scientists are taking, and that you can relay in a video, are concrete, publish precise time-tagged datasets, run null simulations for coincidence probability, compare spectra and particle data from the CME comet interaction with baseline comet responses, and deploy field teams to document earthquake impacts and aftershock catalogs. The sensible narrative for viewers: this cluster is scientifically interesting because it is rare and well observed, not because it yet proves a new law of nature. The responsible takeaway: watch for peer-reviewed analyses, follow time-stamped data releases, and treat early hypotheses as testable leads rather than settled conclusions.